We're going to continue rolling along with our program, so please join me in welcoming Shantanu Agarwal to the stage.
Thank you, Alex. Good afternoon, ladies and gentlemen. It's truly a pleasure to be here today. As a direct beneficiary of the Trump-era DOE carbon capture research increases in funding, I can vouch for the quiet climate policy working. So that's something. We're going to talk about one of those breakthrough technologies which got facilitated because of that. That's what we have developed here in Susteon. But before I dive into the technology details, I want to talk about the need for this and why this is so important. So you've seen this chart, all of you, I'm sure, and we talked about it in the morning as well. The 1.5 degrees centigrade pathway is quite difficult, most likely not happening, because we need 2,000 gigatons, and we have got the limit of 2,000 gigatons, and we're already at 1,700 and spending at 40 gigatons per annum. So most likely we can't decelerate enough to really hit that. But likely 2 degrees centigrade pathway is possible. It's something which hopefully the new policy framework which comes out of COP26 signs up to, or something which we can aim for. But even 2 degrees centigrade is a gargantuan task. It is extremely difficult, and it could be very simply another case of what has happened to 1.5 degrees centigrade objective which we had. It'll slip through our hands if we don't follow through very quickly. So we all know about these the green region is basically the conventional abatement technologies, which is all these renewable energy pathways, decarbonization of industry, all these things which we need to do for sure. But one thing which you might be seeing is this brown area in this chart, which is essentially talking about emissions which will continue to happen. This is unabated emissions which we will not be able to control. These are hard-to-abate industries, these are hard-to-abate countries, these are hard-to-abate geological formations which will continue to emit. And for that, we need a net negative emission technology to offset that. If we don't have that, then we'll never get to net negative. We need to solve for that with net negative technologies. And that's what the blue sector at the bottom is. And that's what I work in, net negative emission technologies. So you'll see that this chart for the blue section as well is quite large. And the most conservative estimate talk about 5 gigaton of negative emission by 2050. And 5 gigaton just slips out of the tongue, but it's really a very, very large number. And I'll tell you the scale of it and the enormity of what we need to achieve if we have to do that in a few slides. But let's first talk about what are these net negative GHG emission technologies. Okay. So the potential carbon removal pathways, which we call net negative emission technologies, are either biosphere-based or geosphere-based. And we have heard about some of these in the earlier sessions today. The biosphere-based are available today. They are also scalable today. They're also cheap, $7 to $10 a ton. But the challenge with them is that the reliability and the longevity is in question, especially because of an increasing population size and an increasing climate change. Our ability to control the biosphere-based removal is tenuous. And we cannot just depend on that. We need both and, as Marcella was talking about in the morning. So the geosphere-based negative emission technologies are BECCS, which is bioenergy carbon capture and sequestration, and air capture carbon capture and sequestration. Both of these technologies are quite useful, but are quite early in their development cycle. So they need a lot of work to really scale. We are a believer that air capture can actually, in the longer run, be the right path. Although it is more expensive than BECCS today, it is something which we believe can come at parity and become lower cost than BECCS in the longer run. And it has advantages over BECCS in terms of not competing with food supply or land mass area or biodiversity, those kind of things. So we believe air capture is the right path to really invest in and work on towards creating the negative emission infrastructure for humankind for the future. But let's come back to the 5 gigaton number. So if you're doing air capture of 5 gigaton per annum in 2050, where do we stand today? Today we are at 10,000 tons per annum. And we're talking about 5 gigatons. That's a 500,000x scale. In 30 years, have we ever done anything like this in any industry before? Well, if you think about Model T, when the first one came out, and 30 years later, 500,000 cars came out, yes, we have done it. And so yes, the number is scary, but can be done, and we are really at Model T of carbon capture today. But that's what needs to happen. Electric vehicles, for example, in the last 10 years have grown by 230x. So we have the potential to hit this number, and this number will become smaller if we count the 2024, 2025, 1 million ton capacity which will come online. So by 2025, we'll have 1 million tons of per annum capacity of carbon capture, and then you're only looking at 5,000 times. Still a big number. But what I'm trying to impress upon you is that it is a massive amount of scale which will be required. There is no real way out of this, because this is the sustainable and long-term capture, and it'll also be economical, which I'll tell you how. And there's no reason to run away from it. We should actually promote it, because although there's a large investment required, probably greater than 300 billion per gigaton required capacity, you're also at the same amount creating a lot of jobs and a lot of work, and work for people who are potentially in industries where we want to phase out those industries. These are EPC companies who will have to build these plants. There's 800,000 man-years per gigaton, at least, if not more, required to build a gigaton of capacity of carbon capture. There's thousands, if not millions of jobs per gigaton of capacity. And these jobs are of plant operators, these are of EPC companies, these are of people who are right now deployed in power plants and oil and gas installations who will need alternative ways of employment to use their skills, which they have built in 20, 30 years, deploy here. And this is great, because it also can be used, the carbon dioxide can be used as a source material for fuels. So you can completely phase out fossil fuel and become a carbon dioxide economy in the future. This is the multi-trillion-dollar economy of the future, which is going to happen because we need it. There's no way out. Okay, so who's working on it? There's a lot of people working on it. We are one of them. We track about 29 smaller companies and 3 slightly bigger companies in this space. There are lots of different technologies which they're working on, and all sorts of angles which people are coming at it from, and DOE is doing a great work to promote that. Lots of research funds, lots of investment is happening. We believe solid sorbents is probably the most probable, most likely, most effective pathway. Maybe because we're biased, we are also a solid sorbent company. So, but that's where we see that some of these companies are developing technologies. And what we have developed in our technology is a true breakthrough in the solid sorbent system. And I'll tell you why. So we have a non-amine-based sorbent. Sorbent means the material which captures the carbon, okay? And that is very important because most of the other competitors or the other technologies are amine-based, and amines actually degrade with oxygen. So oxygen is all over in the air. We're trying to capture carbon dioxide. You can't avoid oxygen. So that's one of the challenges which we can avoid with our system. We also have an integrated, very, very interesting selective heating mechanism, which is very energy efficient. We also have low pressure drop. All of these end up creating a low capex, low opex system, which is with a pathway to less than 2,000 kilowatt hours per ton of CO2 in terms of energy, less than $600 per ton a year of capex, and less than $100 per ton of capture cost of CO2, including sequestration. And this is built over tens of years of R&D, which we have done with our team members who have worked on this technology in the past, and then with Columbia University, who is our experimental partner in this technology. So what's different? We call this DAC 2.0. We have worked with a lot of other current players and come up with this new technology, new way to really work with, is because it uses existing supply chains, which is very, very important because we want to scale 5,000 times in the next 30 years. We can't do that by building new supply chains. You have to use existing supply chains because otherwise time will be too long. We are building a factory-built modular unit, which can be essentially printed and shipped and then installed. You don't need to build it on site. That is the way to scale. You have to think about scale on these things because you're talking about 5 gigaton. We are renewable energy based entirely because you cannot have gas being burned and producing CO2 in parallel to doing carbon capture. That's just not good. Even if you're capturing that CO2, it's not good enough. we need to have completely renewable energy-based systems. Our sorbent is more durable, being non-amine, and most importantly, we have the lowest CapEx and OpEx out there, we believe, which can actually make the economic difference of allowing this to scale. The process is, I don't want to talk about it, but basically think about, I don't want to go into too much detail about it, but think about a massive cooling tower with these panes you can see on the left, and the air is getting sucked in from the sides and then being pulled up through this big fan at the top. Okay, so one fan is running like a cooling tower, sucking in air from the sides and then capturing that air in those sorbent materials which are in those panels on the side, and then pumping that CO2 down into the earth. That's what these systems would do. Our bench scale unit is already working. We are building our pilot unit next year. All planning and location is already done. We are looking at building an RTP near our office in Raleigh, North Carolina. And then we are hoping to build a large-scale, hundreds of tons per day, per annum system in 2023, 2024, which will go live in 2024. And this is what's going to look like. These are all little cooling towers. You can see this network of cooling towers sitting on land, which are capturing air and then capturing CO2 from it. The cost curve, as promised, this is the most exciting part. There is not a lot of new science required for this. It's all engineering and scaling cost reduction, which is going to happen. We already believe that our first unit of 100-ton scale is going to be around $175 per ton, and we can get it down to $78 a ton, which is going to compete almost to the cost of some of the point source capture systems. So very excited about that. We've got a team of scientists and engineers, mostly, some business people, and we've got a lot of partners, especially DOE, who has been very, very generous with their R&D support and their continued support with our technologies. We've got 2 DOE grants directly on this technology working with us. So I'll leave you with 3 points. First, we cannot work with just traditional energy technologies. We need to have a net negative emission technology strategy, and we need to run after it at scale now. Second, if we do that, we're going to create $1 trillion business system, which is going to create employment, which is going to create prosperity for our people, and allow translation of skill set with current industries, which are going to slowly phase out. And third, there is a lot of innovation in this happening. We can actually achieve the 5,000x scale, which I'm talking about. And if we just put our mind and investments and policy work towards that, it can be done, but it needs to be done now. Can't wait. Thank you.